In this video, we're going to be discussing Hooke's law. Uh, this law sometimes is introduced in the forces unit, but I decided to just wait on that and introduce it when we discuss energy, because it kind of ties in nicely together. In class, you were hopefully given a couple springs and asked to discover the relationship between the spring force, which we represent as F sub s, and the displacement of the end of the spring. So, or you could also have the compression of that spring, which we represent with an X. Hopefully, after you did the graph, you noted that there was a linear relationship between the force and the displacement, as shown here by this linear line. In fact, if you were careful not to include any extra length, like maybe call this X, um, into your calculations, like you didn't include the length of the spring, you really only considered X as the amount of compression or stretch, in your case, then you should have got a line that nearly went through the origin. And in that case, then you could actually say it's not just linearly related, but the force and the stretch distance or compression distance is directly proportional. So the force is directly proportional to the stretch distance. And that is known as Hooke's law. The spring force is directly proportional to the displacement of the end of the spring. So mathematically on the AP formula sheet, we write F sub s with an absolute value sign equals K times the absolute value of X. This K, if you noticed, was the slope of your line. So in this particular example, we see it's 3.5 newtons per meter. So the spring constant is normally measured in newtons per meter. It basically represents the amount of newtons for every meter of stretch. Conceptually, hopefully you're thinking that represents basically the stretchiness of it. It's how stiff it is. The stiffer that spring is. So if you have like a steeper line like this, right, that means the spring is stiffer. It'll have a higher slope and it'll have hence a higher spring constant. Now, technically speaking, the equation is not written this way. It's just written this way because it's easier, because a lot of people confuse the actual equation, which is written over here. Technically speaking, the equation actually has the spring force is equal to negative k times x, or you could just simply write F sub s equals negative kx. But that can be misleading to many people because of this negative sign. So let me try to just point out why there's a negative sign in here. Let's take a look at this example shown here to the right. This spring is being compressed by this hand to the right with a force F. And it's being compressed to the right with this distance x. And as you, by the way, if you notice too, hopefully you notice this, he's not applying the same force. The force is actually getting bigger as you're stretching it more distance. So the force is not constant. It's getting, as you compress that spring more and more, you're applying more and more force. But actually, let's get back to that negative sign. The spring force in this case, the spring force is not really this external force that's shown. It's actually the force that is to the left, right in here. This is actually the spring force. The spring force is really, the spring's trying to restore it by pushing the spring back to its equilibrium position, back to the left. This is equilibrium, by the way, over here. So really, as you compress it to the right, say 10 centimeters, the spring is going to, this is all in equilibrium. So one force is being applied to the spring to the right by your hand externally, and then there's a force for keeping it from sliding it to the right, which we'll call the spring force, and that's to the left, and these two forces are equal to each other. So the spring force is actually to the left, even though the compression is to the right. So really, in essence, that spring force is in the opposite direction of the compression. So hence, opposite being negative sign. Okay, go ahead and start doing the next example.